So let us first understand that there are three types of motion in an aircraft. So this motion is called rolling, yaw, pitch. So you have to be very familiar with these three terms before we go into effect of gyroscopic couple on aircraft. This is rolling, yaw, and this is pitching. Okay. So these are the three possible rotations. As I already told you, when you already have one rotation and you apply the second rotation, you will get the third rotation as a resultant reactive couple. So that is gyroscopic couple. Here, first assumption we make is, before going into this derivation or whatever formulas we see, this assumption is that you have a propeller in the front, or even jet engines also have compressors and turbines rotating, always rotating, right? There is a rotating propeller in the front. Now that rotation is always there. With that, when you try to turn the aircraft in one side, the third reactive force will also come. So about the green axis, your propeller is always rotating. So that is the first assumption. So the remaining, if you give blue, you will get red. If you give red, you will get blue. Clear? Effect of gyroscopic couple on aircrafts. The top and front view of an aeroplane is shown below. Let the engine or the propeller rotate in clockwise direction when seen from the rear or tail end of the aircraft, taking a left turn. Okay. So omega equal to angular velocity of the engine radians per second, k equal to radius of gyration of the propeller, m equal to mass of the engine and the propeller in kilogram, r equal to radius of curvature, the curve that you are taking. I am going to take a turn. Now what is the radius of that path I am traveling? That is capital R. Okay, I equal to moment of inertia of the engine and the propeller, linear velocity of the aircraft, let us say 500 kilometers per hour. What is the linear velocity? Omega p is the precisional velocity that you are going to generate. The gyroscopic couple acting on an aeroplane is the same formula, I omega omega p. Before taking the left turn, angular momentum vector is represented by OX. Okay. So when it takes a left turn, the active gyroscopic couple will change the direction of the angular momentum OX to OX dash. Vector XX dash in the limit represents the change of angular momentum of the active gyroscopic couple and is perpendicular to OX. Thus, the plane of active gyroscopic couple XOY will be perpendicular to XX dash. See, it's very simple. Okay. So when you take an aircraft with a propeller going around in clockwise direction and take a left turn, your nose will go down and the tail will go up, something like that. Clear? So we'll have a tabulation of that. So all these by applying the right hand screw rule, all these technical things, okay, they will explain a lot of stuff. It's very easy to understand, but okay, the reactive gyroscopic couple will act in the opposite direction. Okay, so the effect of this couple is therefore to raise the nose and dip the tail of the aircraft. When your propeller is going around in clockwise direction and you are going to take a left turn, what will happen? Okay, let us say this is my propeller, front view of the aircraft. Okay, I am looking at the aircraft from the front. This is my propeller. Okay, the propeller is rotating at a very high speed in clockwise direction. Now, when the aircraft turns left, what will happen? Your what is this couple direction? When you go right, your nose of the aircraft will go down, tail will go up. That is effectively your flight will go down, nose dive. Okay. Same thing, anti-clockwise spin of the propeller if you take left. Okay. Your nose will go up, tail will go down, your aircraft will jump up. Clear? Very simple to understand. See, you just keep two half arrow marks. Clockwise rotation means what? You are looking at the aircraft from the front. When you take a left turn, your aircraft will go down. When you take a right turn, your aircraft will go up. That's where your arrow mark is pointing, right? Very simple. Anti-clockwise rotation. I am looking from the front. Okay. When aircraft takes a left turn, it will go down. Right turn, it will go up. It's that simple. Okay. So that's what these people are trying to explain with a lot of things, right? When the aeroplane takes a right turn under similar conditions as discussed above, effectively you have to dip the nose, raise the tail. So there are various conditions. Now what I have done is I have made this very short in form of a table. Okay. So propeller rotation, when the propeller is rotating in clockwise direction, when viewed from the front, Okay, not from the pilot seat. When viewed from the front, my propeller is rotating clockwise, and I'm going to take a left turn. What will happen? The front of my aircraft, that is nose of my aircraft, will go up like what is showing now in the animation, and the tail will go down. Okay, similarly same clockwise rotation, right turn, my nose will go down and tail will go up, right? Anti-clockwise, the opposite. If you are going anti-clockwise direction, take a left turn, your nose will go down, tail will go up. Similarly, anti-clockwise, right turn, nose will go up, tail will go down. So the easiest way to remember this, so just do a split circle, clockwise rotation, anti-clockwise rotation. Okay, so from the center, if you go to the left, your flight will go up. So this is clockwise, left turn. In a clockwise, if we go left, what does the arrow mark point? Upward. So nose will go up, tail will go down. Same clockwise, go right, your nose will go down, tail will go up. Similarly, come to the center of the anti-clockwise, split arrow mark, go to the left, arrow mark point downwards, nose will go down, tail will go up. Anti-clockwise, left, nose will go down, tail will go up. Similarly, right side, pointing, this arrow is pointing upwards, so nose will go up, tail will go down. Clear? It's that simple. Just with this split arrow marks, you can tell everything. Same thing can be applied to the next portion or the next part of the ships also. So it is very, very simple. You don't have to remember a lot of derivation formula, everything. Just do a half circle, take a left turn, the arrow mark points down. So that whatever arrow mark pointing is applied for nose. So when nose go down, the tail will go up. Take right, nose go up, tail go down. Similarly, clockwise. Take left, nose go up, tail go down. Take right, nose go down, tail go up. That's all. So that is the end of gyroscopic effect on aircrafts. So this is taken from a Kurmi textbook 14.4 section.